This class is sort of a continuation of where we left off last time. We're going to finish up text analysis. We sort of started with tf-idf. This class we're going to use tf-idf, and I'm going to show you how Google News is built. I'm going to show you how Overview is built, which is this investigative journalism document mining system that I've been working on for a number of years. We're going to do all kinds of fun stuff. What am I forgetting? Oh yeah, word embeddings. You've probably heard of word tf-idf, yeah? How many of you are in the NLP class now? Okay, yeah. You were. Okay. We're also just going to talk about what's hard about doing NLP in journalism, because what you study in your CS classes often won't work for the problems that we have in journalism. I'm going to show you why. And hopefully you will be among the few, the brave who solve these problems in your careers. All right, so here we go. Overview is a system I've been working on for about 7 years. And it started in 2010, December 2010, when I was at the Associated Press. And this was a couple months after the very first major WikiLeaks releases. These were the Afghanistan and Iraq war logs. Does anybody remember these? Yeah. So these were very interesting documents. Let me pull one up, actually. So WikiLeaks, Iraq, SIG Act. I think they still have them online. Yeah. Here we go. So if I open one of these up, this is what they look like. These are structured data. So they have, things like location and, how many people were detained or killed and so forth. And then they have this full text field, right? This sort of free text description of what happened in the event. And at the time that I started looking at this, a bunch of news organizations had done analysis of the statistical part of this, right? So people had drawn maps of where people were killed. They had drawn charts showing the number of wounded and killed, and especially civilians killed, which was a topic of major interest at the time, over time. Nobody had really done big analysis on this type of stuff. Sort of individual events had been analyzed, but I wanted something more than that. So I did this visualization, which is in the notes for this class, at the end of 2010. And I took 1 month of these things, and I turned them into tf-idf vectors and used cosine similarity, and created this like poster-sized image, which if you zoom way in on this, what you can see is that each, wow, it won't let me go any bigger than that. Oh, there we go. There we go. So each dot is a document, and each document is labeled by the top 3 words according to tf-idf. So I'm trying, it's sort of a summarization technique, and we'll talk about summarization techniques more today. And then what I did is I computed cosine similarity between every pair of documents, and anything which had greater than, I think 0.6 is what I used, I drew an edge between, and the heavy edge means they're more similar. So for example, these thick edges here, media, reference, spot, these actually might be identical documents because they're 3 with the same keywords, right? And then I colored them by the structured data that were already in the reports. Right, so I didn't classify this. This is data that was already given. And what you get is this overall pattern of, see all of this blue here? This is all criminal events. what you get is actually that most of what was going on this part of the war, so this is December 2006, was classified as criminal events, meaning that those were things that the coalition military was not involved in. And so what you're seeing is a picture of the height of the Iraqi civil war. And it's pretty nasty stuff. If you zoom in on this stuff, you can see, I've labeled some of the big clusters just manually, right? So this is a theme you're going to see a lot.
Most common words within those clusters?
They're not. Yeah, they're not really the most common words. They're sort of the most interesting words, right? So they're human annotations on these clusters, although often those words are common in there.
And the labels, when you zoom in on each document, is given by the document itself?
tf-idf, yeah. Right, so this is, I think this is 12,000 or so documents. We run tf-idf on the whole thing. Then we take the words in each document that have the highest score. So there's some combination of very common in that document and very uncommon in other documents.
What is the position on the chart?
Very little. So the layout is done with a standard, you've probably seen like force-directed layouts. Yeah, so it's that type of algorithm. And I talk about this in the post, which you should read if you really want to understand what's going on here. The position on the plane doesn't mean anything at all, because we don't derive that from the data. The distance between any set of points is significant. So really the only thing you can read off this chart is, are two incidents close or not as measured by cosine distance? Yeah.
How did you explain the concept of cosine similarity, or how did you explain what this visualization means to a general audience when this was published?
So it wasn't published as an AP story. It was published on, as a sort of blog post saying, hey, the AP is doing this type of research. I'll show you. We used this technique to produce another story, but.
So this was more of like a nerd blog?
Yeah, exactly.
Okay.
This was a sort of proof of concept that we could get something out of analyzing the text. And indeed, one of the things we got out of this was this cluster, which is, this is everything with tanker trucks, and they're classified as red, which is explosive hazard. So all of this red stuff in the map is the IED attacks, and they're mostly sort of scattered around. So there's not a lot of linguistic similarity between the descriptions of those incidents, except for this. And so this is several dozen incidents involving a tanker truck being blown up or used, threatening to blow it up. Yeah.
So you were just like looking at this data and you were individually inspecting each cluster before those labels were assigned, right? Like you just saw this cluster, like what's going on.
The big labels are manual. Yeah. Right. The small labels are generated by the computer. The big labels are manual. You could have algorithms that label the cluster. In this case, we didn't. Yeah.
So this was a backwards model.
Yeah.
And I see that there are a lot of like numbers from the tf-idf stuff.
Yeah, that's because there's a lot of numbers in the text. So if you go look at the text, right?
Yeah.
I actually don't know what they're talking about.
Yeah, I was just asking why you didn't take them out, because I guess they were like ID numbers for something or the other. So.
Yeah. So you could take them out. I think overview takes pure digit strings out. But this is one of the many types of questions you get when you start doing tokenization stuff. So then I went through the AP archives and I found most but not all of these incidents. I was actually able to match these up to stories. And potentially you could do a story about, tanker trucks being destroyed, either used as a weapon or to prevent fuel supply and so forth. I also think it's interesting because it's a measure of coverage of AP reporting, right? I'm always curious, in something that's chaotic in a war, do the wire services report a single person killed? And actually, Human Rights Data Analysis Group has done a tremendous amount of work on exactly this question, and comparing different sources and trying to model how likely it is that a particular event will be covered. And it turns out that almost every casualty in that war, and we're talking 100,000 people, right, was covered by some media somewhere. Right? There's a bunch of news organizations operating, and usually at least one of them got it, and very often two or more. So I was actually kind of impressed to discover how thorough the record is, although you really have to do a lot of work with multiple sources to get a good record. So this is where this sort of tf-idf journalism adventure started for me. Yeah.
Were there any other stories that came out of this visualization, any other correlation that journalists hadn't seen before? Apart from the fact that this showed coverage that was already existing.
Not really. So we didn't get a story out of that visualization. That work was the proof of concept that led to the development of Overview. We were like, okay, there's something here. We can do something. This led to a prototype. And I guess I'll just play the video. This is the prototype being used to produce a story, and I'll talk about the story in a second. But I want to show you the video, in part because it's going to demonstrate a couple things. So this here on the right, this is a multi-dimensional scaling plot of tf-idf vectors, and this is hierarchical clustering based on those same vectors. Right, so there's both techniques that we looked at last class. And so you get to hear me narrating a video from 6 years ago, it even tells me. This shows you what Overview can do. Here we have the main interface to the program, and we'll go through these one at a time. But right now what I want to point out to you is this plot. Each of these dots is a document. And if I select one, Overview will load the source web page. And so I can see that this is a particular press release about drilling for oil. I can see over here where it appears in this tree as well, and I'll get to that in a second. But the first thing I want to show you is Overview's clustering algorithm. So if I press the cluster button, after a few seconds, it sort of sorts the documents into similar groups. So remember I told you that MDS is like modeling all the documents connected by springs and then energy minimization. So you can literally do that. That is literally what's happening here. Each of those documents starts in a random position, and then it applies spring forces between every pair to move them until they eventually settle down and sort of reach a low energy configuration. And of course, it'll be a local minima, right? The configuration they reach will vary depending on where they started. But clusters are preserved structures. You're always going to, the same clusters will always appear, but they might appear in different places. Yeah?
When you mentioned force-directed layouts earlier, is that like a similar principle?
Yeah. Yeah, it's exactly right. So this is exactly a force-directed layout. There's just some optimization to make it run with large numbers of points. There's some cheats that we can talk about if you want. You don't actually compute every pair of forces because that would be impractically slow. You do some sampling and some hierarchical stuff. And the first thing to notice is that they're all kind of in this blob, but there's one way out here. If I grab all of these, what I can see by looking at the documents is they're all in Spanish. So the first thing it's done is said, okay, there's a group of documents that's really different, and in fact, they're really different because they're all in a different language. So I can take these and I can create a new tag to record what I found. Spanish, and we tag it. Over here in the tree view, the tree is actually just another display of this items view here. So as I go through the branches of the tree, I can see that they correspond to clusters that are in the items plot, but we can't necessarily always visually pick them out because they're sort of smushed together. As I start going through these, I can look at what's in each of these. This is a display here of the different nodes in the tree that I've selected. And what I'm looking at are the top keywords in each of those nodes. And then this is the actual document. So if I look at the keywords here, this all seems to be about the Iraq War, but then some children's stuff too. And actually what's happening here is the left branch is about the Iraq War, so I'll create a tag for that. And then the right branch has to do with children's health coverage. So if I actually view one of these documents, I can see what he's talking about there. And so now I've created these two tags, and if I look in the tree view or the cluster view, I can see that these correspond to little regions. So I can go through continuing this way. So this was the basic idea, right? You had these two views, and we didn't really know which one would be the most useful. And they both showed cluster structure in tf-idf space. And the idea is that you could quickly analyze the topics of a document set in this way. All right, so far so good? Okay, so that was, this is what it looked like in early 2012. When I was working on this story, I think I showed you this last class, yeah? I got these 4,500 pages of documents. You saw one of them you've seen some screenshots of this material, and you'll see a few more. They're nasty documents, so I like to look at them. The reason I called the system overview is because I was very interested at the time in doing a type of story which is sort of a summarization of a large amount of material. This was a type of story that was very hard to do at the time. Right? So this was the WikiLeaks problem, or the problem with these document set. So for example, if I open one of these up, June 2, there we go. So here's one of the original PDFs that this came in. And it just sort of goes on and on. You can see there's a few different report types. There's some email. This is a fun one. These are, again, all of the reports of security contractors drawing their guns. And you can always read the individual stories. There's some fascinating stuff here. This is a policy document. There's individual incident synopses. So it looks like people shot at their motorcade. And in fact, what I discovered was that that second paragraph here, the nut graph, right? Mostly these contractors fired at approaching civilian vehicles to protect U.S. motorcades from the threat of suicide bombers. The point of, or what ended up being sort of the main point of this analysis, was to get that mostly. This is a stack of paper this thick, and reporters had read individual incidents, but I wanted to be able to say something about the group as a whole. And so what I did is I used Overview to cluster the documents into topics. And you can see some of the topics here, right? So HN injury. HN is host national, so that's Iraqi civilian injuries. Those actually didn't tend to cluster very well because the language that was used to describe them wasn't similar enough that they grouped together. But as I read other things, I tagged them. But things like IED or Marines or motorcycle, they tended to cluster just because you would get language around the Marines or language about motorcycles. So the idea here is that the clusters that I built are based on but distinct from the clusters that the algorithm builds, right? And so I've sort of got this layer on top of what the algorithm is doing where I can refine the choices that it's made in whatever way I need to do my reporting. So that was the sort of baseline technique I used to explore all of this material. And then I did a few other things. So how did this story work? So it worked like this. So I started with automatic clustering. And that gave me the sort of first pass, what's in this document set. And then I used manual tagging, or you can think of it as manual clustering, right? That gave me sort of semantically rich groups of documents, the categories that I'm interested in as a reporter, which is not necessarily the categories that cosine similarity is going to find. And then the last stage I did was random sampling. So I was pretty sure by looking at the size of the clusterings and my tags and so forth that the majority of the incidents were shots fired at a vehicle approaching a motorcade. But you know, this is the Associated Press, you have to be right. And so what I did was I wanted to prove that that was the case. So I took a sample of 50 documents, just because it was a manageable number. By the way, it was 4,500 pages. It ended up being like 670 documents. So I actually wrote code to try to identify the cover pages and split them. That was a big problem as well, as to reconstruct the original documents from the page sequence. That's a major unsolved problem in doing this kind of work.
I don't understand why reconstructing it is, if you could just...
If I could just...
You said that it's reconstructing page documents into the original document was something you had to solve. I didn't understand why.
Oh, what's the problem? Well, look. So this is just, the material came in, I think, 6 different files, each of which was, 500 to 1,000 pages. And so this file, this PDF file, here's an incident report, right? And so it starts there. It goes on for, in that case, that's it. That's the end of it. So here's another document. It's some email. Here's an engagement report. These are all one-page documents, but many of these documents go for multiple pages. So there you go. There's one that goes for 2 pages. So the problem is to take this sequence of pages and turn it back into the original incident reports or sort of other types of reports that you have. So for example, this runs for a couple of pages. Oh yeah, you get handwritten stuff too. Fun, good times, which of course we don't pick up at all. But so that would be a 2-page handwritten document. That would be a 2-page handwritten document. That would be a 2-page form, 3-page form. So the unit of analysis I wanted to use was a document. And so to do that, I had to reconstruct documents. Now, you can make the argument that maybe the unit of analysis should be paragraph or page or incident, all of which you would reconstruct in different ways, right? So that's one of the things that you're going to face on your homework this week is what is the unit of analysis. Anyway, sampling. So I took these 50 random documents, and then I just read every one of them, and I wrote a little spreadsheet. And the spreadsheet had a bunch of columns. It had, in this case, it had, is this about protecting a motorcade? And was there a civilian injury? Right, and so I just read each of these documents and I tagged them, yes, yes, no, whatever. And then for the motorcade, what I ultimately wanted was a percentage. And I can't remember exactly now, but it was something like 70% of this sample, which I felt justified the use of the word most. Or here's the story, right? Mostly these contractors fired at approaching civilian vehicles. I mean, all kinds of crazy stuff happened. It's a war. But that was the dominant story there. And this goes on for several pages, right, and talks about a lot of the crazy stuff. And then the civilian casualties, what I did is I used this to get an estimate. So I think I actually saw 2 in here in my sample. And when you work out when you take that as a proportion and multiply it through, you get 12 incidents. It predicts 12 injuries. And I had, in fact, found 11. And so that was a check that, even though I hadn't read every document, my search technique for finding civilian injuries, which included looking through the clusters and included just manually searching for words like injured or ambulance or killed or whatever, had actually found most of the incidents. Right. So I took this 2, and I turned this to implies 12, and I think it was like plus or minus 4 injuries, right? And that was a sanity check on my searching for these things through a variety of different techniques that said, okay, maybe you missed 1 or 2 or 3, but you didn't miss 10. Now, missing an incident where someone was injured is, there are worse things in terms of the effect on the story, right? The story is still true no matter the number of incidents of injury that are actually in it, because the way the story is written, it just says, we found these incidents, and then I had a link to each one, right? So that's always going to be true. And the language was, you can think of it as sort of saying at least. You'll see this a lot when you're doing these sort of like find something in a big pile of documents, this like at least language. But if I missed half of them, I really want to know. I actually suspect that I haven't missed any. No one has since found any that weren't in that original list. So in other words, I'm combining a bunch of techniques, right? So random sampling, and there's one more that I'm combining here, which is text search. I'm putting all of these together to get these various types of quantitative results in the document set. All right, so far so good? Okay, so that was the first story that was done with overview. The next thing we did was, we got a grant from the Knight Foundation, which allowed me to hire some folks and start really building this out. The prototype was mostly unusable. And we built it into a web app instead, and this was the first pass From our user tests, we found that people weren't really using the scatterplot view, and so we just saved ourselves some time and avoided it. I kind of miss it now. It was a cool view. And it's useful for this class to try to teach people what document vectors are. So we had this hierarchical clustering algorithm. And you can see, in this part of the screen, these are documents, and it's showing you the keywords, top keywords in each document based on tf-idf in the selected cluster. And then these are, again, this tagging system. And then we built a document viewer into it again. And it was still too complex for people to use. The clustering algorithm wasn't great. It tended to produce lots and lots of small clusters, but that is hard to avoid because it turns out, half of the documents aren't really like any other document. There's a lot of unique stuff here. And then we redesigned it after a bunch more user testing and changed the clustering algorithm. And then a reporter named Tyler Dukes, then at WRAL in North Carolina, used it to do a story. Same sort of deal. He got a document dump from a FOIA request, also about 4,000 pages. And this was on the issue of state government delays issuing food stamps in the summer of 2013. And what they actually did is they filed a FOIA request to a bunch of different county governments. Only some of them responded, but in one of those responses, he discovered, using overview, this cluster, that tag NC direct. So that little label, most NC direct, means that I think the threshold for most is 70% or something. It's telling you that this is a very common word in these documents. That is a government mailing list all through North Carolina. So even though they only got a few counties responding, Overview found and clustered all of these documents from the mailing list. And then on the mailing list was discussion of this bigger issue. And it turns out the problem was web browser compatibility. It's like you couldn't sign up for your food stamps on Chrome or something. And this was the resulting story. So tens of thousands of people went hungry. So, I was glad to see this being used to produce an important story. To me, though, the most interesting thing was, as opposed to this type of cluster where the documents have a topical theme, right, which is what I had sort of imagined the point of doing this type of analysis would be. In this case, the cluster, they're not really related by sharing a topic. They're related by all being from the same mailing list. And they ended up being clustered because they all had the name of the mailing list in the subject line. Right? So that was a lesson to me, is you think you're doing topic analysis, but actually you're analyzing you're just counting words. And so this word NC direct just appeared a lot. And so that became the basis of a cluster. And so think about running cosine similarity on these types of forms, for example, right? Now, you kind of imagine that you're going to run your fancy NLP topic modeling algorithm, and we're going to look at such algorithms later this class. And it's going to come up with some classification like, black four-door sedan was traveling through the stopped traffic at a high rate of speed. You sort of imagine or hope that it's going to come up with the category that's something like fast-moving car, or maybe stopped at traffic light, or hand signals or something. Who knows, right? Something like that, something interesting. But probably what you're going to get when you classify a pile of these is you're going to get a pile of documents that in a cluster that has sensitive but unclassified, or maybe Bureau of Diplomatic Security, or maybe spot report, right? Because these words are all equally important to tf-idf. It doesn't know, right? So if you cluster a bunch of forms, maybe you sort of imagine that you want the content of the forms, but what you end up getting is that it puts all of the forms of the same type in one cluster, which can be useful. But that was just a lesson to me about, okay, the way I'm thinking about this stuff is not the way the computer is thinking about this stuff. Okay, questions so far?
Yeah, I'm just curious how does MDS translate into a hierarchical cluster?
Well, MDS is not a clustering algorithm. It just lays out, it just puts points on a plane. That's all it does. The hierarchical clustering was...
That's a separate...
Yeah, exactly. But you expect to see structure that matches between the two, right? So you expect that a cluster that you find in the clustering algorithm will also be a cluster on the MDS plot, which is often but not always true for various reasons. So, all right, so he did that story. And then there was this story. This story was a finalist for a Pulitzer Prize. This was Adam Playford and others in then at Newsday. And this was based on an analysis of a bunch of documents. There was internal police department documents, but actually the part they used overview for mostly was an analysis of proposed and passed legislation at the county level. And what they were trying to find out is, so this is a story on police misconduct and the lack of consequence for it. And what they used overview for was to prove that there was never any proposed or passed legislation that addressed police misconduct. So what they used overview for in this case is they ended up clustering by, it ended up clustering by bill topic. So they were able to throw out whole swaths of bills and be like, okay, these are, here's 10 bills or 20 documents. There's actually only 3 bills here. There's just lots of versions of each one. And, I've read the first few paragraphs of each of these 3 bills and I'm done. So it was kind of like a fast way to analyze whether you needed to look deeper in a cluster. So this sort of cluster filtering was one way they went through this. The other way is they used text search again, which by this point we had added to overview. Early versions did not have search in it, which we discovered that users absolutely had to have search. But again, it's this triangulation method, right? So they searched for words like police and then read all the bills with police in them, which is one way to see if anybody had addressed police misconduct. And then they also went exhaustively through the piles of documents. You can kind of think of the point of overview, or one of the ways I used to think about it was, I'm trying to build a system that lets you avoid reading every document. So that's the idea. This is what it looks like today. I keep the system up and running at overviewdocs.com. You can also run it on your own computer. It's an open source thing. When you first run it, what you actually get now is a word cloud. That tree still exists. You can see it in this picture here. But it is no longer the default view because what we've found is that document clustering is only sometimes the thing you want to do. And it's also hard to describe what the clusters are, right? We've spent a lot of time talking about how tf-idf works and so forth. And the first question that reporters asked when we showed them the tree was, how does it decide whether a document is in this cluster? Because if they find a cluster that talks about oil wells, how do they know that all of the documents that talk about oil wells are in that cluster? And the answer is you don't, right? And this is why. So here's the issue with clustering. And this is not a problem specific to overview. This is just a problem with the whole idea of document clustering. Is that there's going to be a potential mismatch between the topics that the reporter cares about and the topics that the clustering algorithm picks up, right? So if I have the words oil well, and actually Overview uses bigrams for some of its analysis. So if I, oh, that's not live, but this is live.
Wait, this one seems.
No, okay. So here's our favorite press releases again. So here's the topic tree. And, oh yeah, see there, new _ Jersey? It's actually picking up common bigrams as well. So it actually does this 2-word analysis. So if I have this bigram oil well, and it appears in 2 groups of documents, right? So I have this one document, or one set of documents that, say, is on climate change. And I have this other group of documents that's on, let's say, mining rights. And these could be very different documents. These could be a bunch of court cases. This could be a bunch of scientific studies, right? They could be really about different things. And both contain the word oil well. And depending on sort of the details of what words are in these documents, these could all end up in the same cluster, or this could be a cluster, and that could be a different cluster. Like, it's not really clear how all of these are going to break out. So when a reporter finds a mining rights cluster that has the word oil well in it, and they ask, well, is this all of the documents about oil wells? I mean, you have to say no, because there could be documents about oil wells in some other cluster, perhaps a cluster that's relevant to them. So that's why text search is still interesting. And what Overview actually does is if I search for oil, it shows the fraction of documents in each cluster which contain that. And you can see, here you go, most oil. And then I can open up that. So this is a hierarchical clustering. And actually start reading some of these documents. Oh, well, I'd have to actually open the original one if I want it in HTML. There you go. So that is part of why the default view is now word cloud. Word cloud has the enormous advantage that everybody knows exactly how to interpret it. So if I click on the word energy, it's going to get all kinds of random stuff. And you can see here that it's cutting across different tags. So here's all of the tags that I have, right? So there's all the airport stuff. Oh, and it doesn't have any energy stuff in the airport tag. But at least the reporter is going to know, they're going to be able to model which documents are included and which documents are excluded. Other things that we have in Overview now, so everything that left plain is a plugin. You can write your own Overview plugins. We've got some entity extraction, which actually does not use any of the algorithms we're going to talk about later, and we'll talk about why. And this thing called multi-search, which just lets you search for a whole bunch of stuff at the same time and then do intersections of the two. So I can set any one of those search terms as a filter. I guess in some way I was disappointed that the more sophisticated techniques weren't more useful. But I think what I had to learn was that you have to get the basics right before that stuff is. Okay, I think that's the end of our, that's the end of our discussion of Overview. Questions on that before we move on? Yeah.
The entity extraction is just regex?
Kind of. What it actually looks for is, it has a bunch of different methods. So there's some dictionary methods. So it will look for things that are in the geonames database to find places in multiple languages too, right? It's part of the reasons we did this. Hey, glad you could make it. And then to find company names, it looks for sequences of words which have a capitalized first letter and end with a company suffix. Right, so LLC, GmbH, Pty. Again, we were working with OCCRP, which has documents in like 18 or 19 languages. And so part of the reason we did these really simple algorithms, is that they had to work multilingually. And at the time, and even today, there's not very good open source multilingual entity extraction. Standard entity extraction like NLTK style or Spacey or any of the libraries actually has some pretty serious problems for journalism, which we'll talk about a bit later today. Okay, yeah.
I had a question about, like you were talking about how you really don't know how it clusters things together when you want to like pick out topics. So if someone were to like figure out some patterns with overview, they would still have to fact check that every document. If they want to say something assertive, they would have to fact check each document to make sure that it's in the right context. Or do you think then you could apply something else to see that, well, these sentences always occur in this particular context, so we can, it's always like.
Right. I mean, so this is why I use sampling on the Iraq story. Right. It was a way to verify the conclusions I had reached from doing the clustering analysis. In practice, what people tend to do is you'll use the computer to pick a set of documents, sort of narrow it down, and then manually read all of it. We don't, there just aren't any techniques that we have enough confidence in to let the computer make the final call. And this is a pattern we're going to see over and over again, yeah.
Do you use anything other than tf-idf embeddings? Or?
Not an overview. Other people have used them in other things. And, we could put them in there. Yeah, we'll talk about other embeddings soon. Okay, so that's overview. Next, we're going to talk about this thing called News Blaster. News Blaster is, I think actually they just stopped running it. The system is no longer live. It was built at Columbia in the early 2000s. So it's quite old. The reason we're talking about it is that it is a publicly documented news aggregation system. So in your references, there's a paper that describes the architecture of this. And it's a very standard architecture. If you're, so Google News is way more sophisticated than this, but it's built on the same principles. And if you're going to build a news aggregator, you have to go through something like this. So this is what it looks like, or looked like. It scraped a bunch of sources. I think it had a couple dozen sources. And first it clustered articles. So, all right, Omar Khadr returns to Canada. It's saying 5 articles. So it figured out that these 5 articles are talking about the same event. And then it put them in the world category. And then it also summarized them by producing this headline. Whoops. So we have a bunch of problems to solve here. Here's the basic pipeline. First, we have to put things in events, and then we have to split them into topics. And their topics are fixed. It's like world and finance and sports and something, business, I think. And then summarize. So the first question we have to solve is how do we decide whether to, the first thing we have to solve is scraping, actually. And scraping is a pain. As any of you have tried to get the text of articles will know, it's actually quite difficult. And what they did at the time was very simple, is they just took the largest text field off the page. Might still kind of work. Today, there's a bunch of APIs, some of which are built into your browser. You've got this little reader view button, which pulls out the text that way. That used the now defunct readability API. I don't know what they use now, but there's still public APIs to do this. There's one called Mercury. It's a non-trivial problem to get a standardized feed of articles from a wide variety of news sources. So this is what a lot of the architecture is going to be. And we're not going to say too much more about it. But the next step is clustering of events. So given the text of two stories, how would you decide whether they refer to the same actual event in the world?
A date.
Hmm?
If there's like a date or something.
Yes, you can definitely use the date, yeah. But lots of things happen on the same day.
Same people mentioned, places.
What's that?
Place or people.
So you could do entity extraction, and then what, though? So now you've got lists of entities for each document. Cosine similarity, yay, yeah. So, right. That's, yeah, there's a plan to all of this, I swear. Yeah, so it's exactly what we've gone through, right? It's tf-idf and cosine distance, or cosine similarity. And then hierarchical clustering. There is one interesting wrinkle, though, which is that, so we looked at k-means, and there's a bunch of clustering algorithms. All of those algorithms assume that you start with the complete set of documents. And you don't, because here the documents arrive one at a time as the stories are published. So instead what we do is this greedy clustering algorithm. And the primitive we need to do this, we have almost all the pieces we need to write this algorithm. The one thing that we don't have, which you need for a lot of clustering algorithms, is a function which computes the distance from a cluster to a document. So here's this cluster. It's a bunch of documents. And here's this document. And you want some sort of measurement of well, how far is the document from the cluster? But how do you do that? Because we've only really talked about computing the distance between documents, not clusters. Has anybody gone into clustering algorithms and know how we do this in practice?
I just asked this question and Popcorn gave me an answer, so maybe she can speak up.
No, I just said that you kind of find the distance across each axis that you have and then find a way to bring it down to one number.
Interesting.
Just like the distance between two 3D vectors, like you find it along the x, y,
Right.
axis and then you bring it down.
Yeah, so sure, that will work, doing it component-wise, but you still have to define the distance in one axis, right? So even in this horizontal axis, there's all of these dots. What distance to what? What is the cluster? It's not a point. Yeah.
You can use like the closest point or the centroid.
Yeah, exactly. So there's a bunch of choices here, right? You can do the distance to the closest point. You can do the distance to the centroid. You can also do the distance to the farthest point, which requires that if you use that definition, then that puts a limit on the maximum distance between any 2 points in the cluster. Right? So these different definitions will give you slightly different clusterings, and they have their advantages and disadvantages. But once you pick one, it's pretty straightforward, right? When you add a point, you find the closest cluster. And if it's within some threshold, right, so you have some threshold distance here. And, if it's less than that threshold, you put it in the same cluster. If not, you start a new cluster, which is this algorithm. And this algorithm this surprisingly simple algorithm actually has some interesting optimality properties. You can prove that this is more or less the best you can do. This is, there's sort of probabilistic arguments that this will work. It's related to an idea called stick breaking, which is like when you make a, never mind. Anyway, so this is the clustering algorithm they use, and they continually build up these clusters. They also have to throw out clusters eventually when the news gets too old, right? You don't show it anymore. And then you have to categorize. So each of these clusters is now a story, right? This is one world event. We set the threshold so that we only get cluster documents in the same cluster if they're the same actual event in the world. Then we have to categorize them by topic. So how do we figure out what topic this event is? Again, the big hint here is we're going to use the same tools. So, any ideas? Yeah, so, okay, tf-idf, but then? What's that?
Do you have to like manually check?
Well, I mean, it's got to be an automatic system. All right, so it's got to, we can have manual work to set it up, but then it's got to automatically categorize the topic of each of these clusters.
We have a list of possible categories and then compare the list with the tf-idf.
Yeah, okay, so we start with a set of categories. So you start with, world, finance, I think they actually call it business, sports, entertainment, whatever. And we'll see other topic categorization systems later that are much more detailed, but say we just have these at the top level. And then we have some new document, and we're trying to figure out where to put it. So how do we do that?
You could train vectors off of, like if you knew what set of documents were already world vectors or whatever, you create a vector off that category from other documents.
Right, so that's exactly right. So what we do is we build the training data by hand classifying a bunch of documents. And so now we have, I don't know, maybe we have 100 documents in each category. And what we end up with is, the world stories are actually this cluster of documents that we have placed in this category. And that cluster has a centroid. And we use that as the representation of that topic. And then we do tf-idf and we pick the centroid, the category centroid that it is closest to. So that's it. It's just the same tools repeated over and over again. This cosine distance idea turns out to be central to all kinds of document stuff. And we're going to look a little bit later in this class on things which are not tf-idf, but we still use cosine distance, right? This vector distance concept is central to not just text processing, but really data science in general. Yeah.
When you compute the centroid, is it like an arithmetic mean or is it a geometric mean?
More or less arithmetic. So computing the centroid's a little bit weird because, as you will recall, we are on the surface of a hypersphere. So if we just do the two-dimensional version, right? So these are actually unit vectors because we've normalized them. And say we want to compute the centroid of just these two. If we just take the geometric centroid, it's going to be here. right, which is not a vector, it's not a unit vector. And so we'll have to renormalize it. Oh no. We have to, the simplest thing to do is just take the average and normalize it. It's what people mostly do. If you want, you can be a little more clever than that. You can take a spherical mean. So that is an averaging operation in spherical coordinates, basically, so you're on the surface. But it doesn't make a huge difference. Yeah?
When you add new points to like the world category, does the vector, do you adjust the vector or do you keep like a static vector to reference?
Well, you don't adjust the reference centroid for the category when you add new things to it, because then the category would drift, right? Which is probably not what you want, because then it could sort of walk away into some random direction. I'm not sure what they actually did when they ran it, but in principle you could update it every so often. Okay, so then the last thing is you generate a headline for this. And we're not really going to talk about summarization algorithms, except we're going to talk about one So what Newsblaster actually did was an older algorithm, because this is now 15 years ago. But instead, I want to show you this. So this is from a recent paper. I think this is now 3 years old, which attempts to generate headlines by training a recurrent neural network. How many of you have done deep learning stuff? Okay. Yeah, so we're not really going to get into it. We're going to talk about it in a few places, but I'm not going to give you a deep learning tutorial, because you can get that in your computer science classes or in about 1 million places online right now. But I'm going to show you the results, which are kind of fun, right? So some of these work really well. UN human rights body adopts reforms. I mean, okay, it's not as specific, but it's accurate. Whereas some of these are just wrong. United set for test. All right, sure. So you can see where the state of the art is. And generally speaking, there are two types of summarization algorithms. There are summarization algorithms that find a sentence or a phrase in the text and extract it. So there you can describe the algorithm as pick a string in the original document or document set that best captures the meaning of the whole set of documents. And that's much better developed and gives much more readable results, because it's just using a real piece of text, right? And the first algorithms to do this actually are from the 1950s. There's really old stuff based on like word frequency ideas. And then there are summarization algorithms which actually synthesize new text, as this one is attempting to do. And these are not very high quality yet. It's really hard to get good text out of them. So Newsblaster uses a pretty simple extractive summarization system. And so basically what it ends up being is it ends up picking a sentence from all of the articles. And normally, so these are news stories, and news stories are, as you are all being taught, written to have a really good, concise summary at the top of the story. So this is almost always ends up being a sentence from the lead, right? So you can think of this as the algorithm tries to find the lead.
How does it pick that sentence? Is like the most? Is it the closest to the centroid, or is it?
I can't remember the exact algorithm it uses. It's not a centroid type thing. It looks at the word frequencies in the documents. So it takes a set of documents in a cluster that it's trying to summarize, and it tries to find a sentence where the words in it are most representative in a tf-idf kind of sense, right? So it's trying to find words that appear a lot in the documents it's trying to summarize, but don't appear a lot in the other documents. So if you're interested, you can read the paper on this. And again, this is a whole field, right? It's an entire series of PhDs on document summarization. But we're going to skip it for the moment. Okay, so that in a nutshell is how a news aggregator works. And this is, to this day, how Google News works, right? So like look at the structure of Google News here. Wow, that's dark. Okay, but so look at these boxes, right? So each of these is a set of stories on the same events. So here's that first level clustering where we use tf-idf, or in this case, they no longer use tf-idf, but something like tf-idf, right? You turn the documents into vectors. Then you cluster the vectors to find events, and then you assign each event to a topic, right? So here are the topics. And actually, the topics get super detailed, right? Okay, I mean, world is a very big topic, but you can have extremely detailed topics. So I'm willing to bet that pumpkin spice is a topic. Oh no, okay, there you go. So these are topics, right? There are people, pumps and systems, it's a news source. I bet like vegan is a topic or something. There we go, yep, vegan topic, right? So the topics are actually extremely detailed, and they are not manually produced anymore, right? They didn't start with a sort of manual list. It's a process of computer extraction and probably manual correction. I actually have no inside knowledge of how they're generating topics, but we've had other speakers in this class talk about how they built their news aggregators and modern techniques. The computer will actually produce a suggested list of topics. But it's the same idea, right? What a topic ultimately is going to be something like a feature vector that you can compute distance to. All right, so that was my how to build your own news aggregator lesson. Thoughts or questions on that? So Google News is also making this choice. What article do I put at the top? And that depends on a variety of factors, including the popularity of that article, including the click-through rate. Also, what news sources you are generally into. So there's some personalization.
How liberal they are, according to Donald Trump.
Yes, how liberal they are, exactly. Although you may see that on my top stories, I've actually got a bunch of Fox stuff. Is there any Fox here? No. There you go. There's Fox. It's because I make sure to read Fox, because I think it's actually important to understand the media ecosystem to read Fox.
I think that top stories are actually constant for everyone.
The top stories are the same for everyone?
Yeah, it's the filter that's personalized.
Oh, okay. What do I get? This is going to be embarrassing. Oh, look, it's space stuff. Space and finance, that sounds right. Oh, yay, TESS is running. It's one of my favorite spacecraft. Okay, so this has been a very technical discussion of what we're doing. In the next class, we're going to talk a lot more about the social, political, and democratic implications of how these are built. What I'm doing in these first two classes is laying the foundations for understanding how these systems are built. So we're not quite up to a recommender system yet. We haven't talked about personalization. So News Blaster is not a personalized system. But in order to talk about how to build a personalized system, first we have to talk about how to build a non-personalized system. So that's where we are in this arc. now we're going to look at some more sophisticated ways to represent the topic of a document. So we started with tf-idf, which is a classic technique. tf-idf has some problems. So if I have a bunch of documents that contain the word HIV, and I have a bunch of documents that contain the word AIDS, and let's say they don't have other words in common consistently, then cosine distance is not going to figure out that those two are related, right? So never mind synonyms, right? So you could also have words that have exactly the same meaning. So obviously HIV and AIDS are not synonymous, but they're clearly closely related, and you probably want to have low distance between documents that contain those words. You might get some relation between those documents if there's enough other words. So HIV and AIDS are going to appear with similar words. So for example, you might have words like clinic and test. And let's say this one has the word health, and this one has the words virus, because you often see AIDS virus, right? And so some of these words are going to match, right? But not all of them. And if the documents are long enough, then you're going to get low distance between these two documents, just because all of the other language is the same. But if the documents aren't very long, or they don't have enough similar words, just because this one has the word clinic and this one has the word test, but there's no words where they overlap, then you could completely miss that these documents are talking about the same thing, right? So tf-idf has no concept of synonyms. It doesn't really understand the idea of a topic at all. What we're going to do instead is we're going to start investigating models that, rather than the feature vectors being words in one way or another, they're going to be topics. And we're going to say that a topic is actually a set of words, or a particular distribution. So in reality, we would say, well, both of these documents are drawn from a single topic, which we'll call the HIV/AIDS topic, which has all of these words in them, right? So obviously it has HIV, it has AIDS, it has test, it has clinic, it has health, it has virus. And then the document vector, instead of giving a score for each word, is going to give a score for each topic. So the first set of methods for doing this was matrix factorization. Oh, I'm motivating this, though. So this is a story in which topic modeling was actually used. This was a Reuters story about which cases get to the Supreme Court, because the Supreme Court is petitioned for far more cases every year than they're actually able to hear. And so they were looking at, well, who are the lawyers who successfully get cases in front of the court? And then what are the cases about? And one of the things they wanted to do was, they started with these 14,000 petitions. They wanted to know, what are the topics of these petitions? We'll get back to this story, and you can actually read about the process of working on this. So this is the idea. We're trying to find topics, and a topic is not a word, right? That's the problem. So one way to describe the problem we're trying to solve is I'm going to give you a set of documents, and I want you to come back and give me a vector for each document which has one dimension for each topic. And I also want you to choose the topics. So I give you a bunch of documents on bicycle repair, and you come back and you say, okay, so the topics in this document set are wheels, brakes, bent frames, punctured tires, and for each document it tells me, this scores a 1 for frame and a 2 for chain problems and a 0 for everything else. And that document is about how to reattach the chain after fixing a bent frame, let's say. So we want to infer both which topics there are and which topics there are in each document. The simplest way you can do this, and the way that the overview prototype that you saw earlier did this, is we just take that set of documents and we sum all of the vectors, the tf-idf vectors in each of those documents. And then you take the top scoring words. So what you can see in this list, so all of this stuff is, these are individual documents, and these are the top scoring terms in each of those documents. And then when we sum the vectors and take the top scoring terms in that sum, which is, by the way, the centroid, right? It differs only by a factor of n from that centroid. So really what we're looking at is the top scoring words in the centroid of that set of documents. Then this is what you get. And it kind of works, right? Firms, mining, macroeconomic, labor, engineers. You can sort of see what's happening here. I think this set of documents was some of the again, WikiLeaks material, the diplomatic cables that at the time the bureau chief in Caracas had asked me to pull every document that mentioned Caracas, and so I did. And so this is some cluster from Venezuelan documents. So you can do this, and in fact you will do this in the homework for summarizing State of the Union speeches. But we want to do something more sophisticated. Oh yeah, here's what I was talking about earlier, right? We want to turn each document into a vector of topic weights. And then to know what are the topics in a set of documents, well, then we just look at the overall topics we got from this process. The first algorithms to do this were matrix factorization algorithms. And this was the idea. The idea was we have the term document matrix. So you all know what I mean by that, yeah? The term document matrix? Okay, that's just word counts, right? So that's just, how does this work? M docs by n terms. Okay, so these are documents, and these are terms, and this 3 here means there's 3 of that word in that document, right? So we're not even talking tf-idf, although you can do this factorization on tf-idf if you want. We're just talking straight term counts to begin with. And we're going to say, well, we're going to approximate this as the product of 2 lower rank matrices. I have to think about this for a second to get the dimensions to work out. Across down. Yeah, okay. So it goes like this. And this lower dimension we're going to call R. We're going to say there's R topics And then this is a matrix multiply. And then these are terms again. And these are documents again. And so what this tells us is what is the, you can think of it as how much of that topic is in that document. And what this tells us is how much of that term is in that topic. So if you multiply these through, all right, so let's think about generating that value there. So we're multiplying, oh no, we have to multiply terms times terms. Oh, I've done this backwards. Yeah, this is totally wrong. I had this right the other way, W times H. Docs by top, okay, so these are the wrong order. Stand by. So again, this is topics. And then this direction has to be documents, and this direction has to be terms. There we go. Okay, that's right. Okay, so if I want this value, I'm like, okay, well, if I take that document has, you know, conveniently a 1 for that topic. That's the weight of that topic in that document. And then that term, that topic has a 3 for that word. So these are the weights of the words in the topics. These are the weights of the topics in the documents. And this is, that's the concept. But this is a purely mathematical expression, right? We are talking about a matrix approximation problem. All we're trying to do is find these two matrices that get as close as possible to this. Because what we're saying, our claim is that you can do this approximation. We're saying that there is latent structure. We're saying that actually if you want to figure out which words are in which document, we can get pretty close by talking about which topics are in each document and which words are in each topic. And then this R is a free parameter. You can think of it as the closeness of the approximation. So here's what this looks like again. You can sort of see how the patterns break down here, right? So, you know, these 4 words are characteristic of this first topic. These words are characteristic of the second topic. And then this document, these 2 documents are mostly that first topic, so they mostly have those 4 words and then so on, right? This is the structure. And we get to pick how many topics. And if you, who here feels really solid about their linear algebra? Yeah.
She has a degree in mathematics.
Yeah, okay. So does singular value decomposition mean anything to you? Okay, so this is very closely related to singular value decomposition. And you will know if you're up on your singular value decomposition that actually you can get strict equality here, right? So I've written this as an approximation, but you can get exact if R gets big enough.
What does that mean?
Right,
I don't know what any of that
in human speak.
Yeah.
So it means this. It means to generate this matrix on the right. You're trying to approximate the term document matrix. I have to sum up a bunch of topics and a bunch of terms. It means that if I add more topics, eventually, if R gets really big, I get to add sort of more. Every time I add a topic here, I'm basically adding another row of term weights into this matrix. And so I can get a closer and closer approximation until eventually, if I have as many topics as there are documents, right? So if I make this matrix the size of this, the number of documents, then I have as many topics as I have documents. And now all I do is I put a 1 on the diagonal to pick one row for each document, and I can exactly reproduce this. Okay, so there's, as I get closer and closer, as the number of topics approaches the number of documents, I can get closer and closer approximation. But the whole point is to not have as many topics as documents. Right? The whole point is to have a much smaller number, because that forces, you can think of it as a sort of pattern recognition. It forces the algorithm that generates these matrices to find sets of terms that appear in the same relative proportions in many different documents. So if I'm trying to closely approximate this term document matrix, if I've, so looking at this picture, right? Right, here's the original term document matrix, and it's like, oh, these terms all appear together in a bunch of documents, right? They're either sort of all there or they're all not, or here they are there at the bottom. So I'm going to say this is a topic, those terms and those proportions. Because if I do that, that lets me make a closer approximation to the full term document matrix. If you have as many documents as as many topics as documents, you've learned nothing, right? If you end up with one topic for each document, it doesn't tell you anything. Or if you say, okay, you've only got 10 topics, find me the 10 word distributions that, if you assemble them together, you can most closely match the actual document set. That starts to tell you something.
And is the single, whatever, mathematical concept important
That's
for us to
math
like figure it out? Like, should we
Yeah.
like know what it is? Or
No, that's one algorithm to calculate this. Yeah. But I just say that so if you do know what that is, that'll convince you that there's an asymptotic approximation here.
Would the smallest R required to get exact equality be the rank of the term document matrix?
Yes. So that's the idea. There's a couple different ways you can do this. There's a popular one called LSI, which is latent semantic indexing. That came out in the 90s. You're going to try it out in your homework. That uses the singular value decomposition. You end up with an odd result when you use the classic algorithm, which is that you can get negative values for these weights. So, like, this document could have -3 for that topic, and this topic could have -5 for that word, which works out in the math because you can add and subtract the topics, but doesn't make a lot of sense in terms of interpretation, because it's a little hard to figure out what it means to have a document that has -5 of a topic or -2 of a word. Right, so remember, this original term document matrix is totally positive. When you approximate it, you might get some negative entries, which is one problem. And another problem is interpreting these coefficients. The whole point of doing this is because you're going to do something with these topics and the topics are, the words in the topics and the documents and the topics in the document. Those are vectors that you would prefer to have everything be positive because it's easier to understand. So there's another algorithm which we're not going to spend a huge amount of time on, but it's called non-negative matrix factorization. And that math at the bottom, what that's saying is that we're going to start with random guesses for the remember, this is the words in topic. This is topics in document, right? Those are these W and H matrices. We're going to start with random values for them, and then holding one still, we're going to pick the matrix that gives, so holding the topics in the document constant, we're going to calculate the words in the topic matrix that gives us the best approximation to the term document matrix. Right, so that's this first step here. And you can prove that, this value for the topics in the document matrix is the closest you can get approximation to the term document matrix when you hold this still. And then you do the other thing, right? You hold this still and you compute that one. And you keep going back and forth, and eventually you're going to converge to the best approximation you can get. So matrix factorization. This was historically the earliest of this type of latent topic model method. Again, latent because the idea is that there's some hidden factor which explains why we get this particular pattern. And the hidden factor we think of as, well, the reason that this document has words like HIV and AIDS and health and clinic and viral and medicine and so forth is because it's about the topic of HIV. It may not have all of those words, but it's going to have a bunch of them. This also handles synonyms because if we have bank meaning money, we're going to have banking words in the document. And if we have bank meaning river, we're going to have river words in the document. And so rather than just having one dimension for this word bank, which was our term dimension, now we're going to have a topic, and the document that is about banking is going to have a 1 here, and the document that is about rivers is going to have a 1 here, and then this one word, bank, is going to have a high value for the money topic and a high value for the river topic, but then the other words in that topic are going to be different between those two. So it handles synonyms in a very natural way, which turns out to be important in a way that tf-idf can't. Right? That tf-idf just cannot represent that this word bank is talking about one thing or the other thing, whereas the topic representation can. The next stage in topic modeling after matrix factorization was a thing called probabilistic topic models. And you get this horrible name, latent Dirichlet allocation. Latent for this latent reason we talked about Dirichlet, because it's this type of distribution that figures in. But here's the idea. What we do is we invent a document generation process, and then we model the parameters of that process. And the document generation process says, okay, we sit down to write a document, and first we pick the topics for that document, which are probabilistic. And so what that actually is the probability that any given word is going to be on any particular topic. So the way we write that is property Z, which is the word, given D, which is the document, or sorry, Z, which is the topic. And then we say, for each word in that, first we pick a topic from that distribution of topics, right? So you think of this as the distribution, and then for each word, we say, okay, well, first let's pick a topic according to that distribution, and then let's pick a word in that topic, which is picking one of these. And we repeat. And the LDA algorithm assumes that the documents were generated in this way and tries to reverse engineer these distributions. Now, of course, documents are not written in this way. This is not how it works. But they're kind of written in this way, right? Like you're writing an article about something, and that something will have certain words. If you're writing about money, you're going to use the word bank, but you're also going to use the word finance. And if you're writing about rivers, you're going to use the word bank, but you're also going to use the word shore. So, this is not meant to be taken seriously as a model of how the text is actually generated, but this is what you're modeling. So here's the idea, The idea is that each document has a topic for each word. And actually, when you run the algorithm, you can have it will actually generate these topics. It will actually give you these colors. And so those superscripts are the topics that that word belongs to. And importantly, the same actual word, like read or bank, could be assigned to, or could have come from two different topics. And therefore, when you run the algorithm, could be assigned to different topics depending on what the rest of the words are in the document, right? It can figure out what that synonym is meaning. So it takes into account context in a way that tf-idf cannot. Here's what a topic actually looks like. So again, this is this distribution, probability of word-giving topic. For some reason, Z is the standard notation. And we put some priors on this whole process to say that we would like each document to have just a few big topics and the rest zero. And we would like each topic to have a few very common words and the rest near zero. So this is where this Dirichlet thing comes in. It's just it's a way of saying, find me a solution to this factorization problem that gives me just a few, it gives me relatively sparse matrices. Because I want to say that my document has, 3 or 4 out of the 50 topics and not like 50 out of the 50 topics. Otherwise, I haven't really figured out what the document is about. So these last few charts are from a Scientific American article on probabilistic topic modeling, which is referenced in your syllabus, and it's a pretty good introduction to it. But this is sort of all of this put together. So on the right here, we have the topics in the document. Notice that some of them are 0, right? And then here's the actual text, and each word comes from a particular topic, and then each topic has a distribution of words. And what the algorithm does is, starting with just the text, it infers the complete set of topics and the topics for each document, and also the topic assignments for each word. Whoa. Okay. So far, so good? And so far I've just given you the setup. Is everyone good with the setup here, the sort of problem we're trying to solve? Any questions about that? I know this stuff is not obvious. It takes a while to wrap your head around. All right. The hope is that when we're done with this, we can read off the topics of each document by looking at these distributions. So how do we do this? Well, the classic algorithm sort of uses the same old trick. You start with random assignments of topics, and you go from there. Oh, this is, let's see, bonus slide. These are the topics for a single word. And you can notice that a few of them peak, but most of them are 0. So that's a constraint you put on the algorithm. That's actually a dial you have. They call it a hyperparameter. And it controls the algorithm's propensity to concentrate the probability mask in just a few topics, or on this side, just a few words. And then notice this stuff in quotes at the top. Those are human assigned labels. The algorithm doesn't generate those. The algorithm just generates a distribution of words. This is a human coming along and saying, oh, that looks like it's about evolution. And so when you run this algorithm, you will find topics that don't seem to be about any coherent thing. That's one of the problems with these algorithms, is that really all it's doing is trying to approximate the term document matrix. It may do that by coming up with rows in this topic matrix that don't mean anything. It just, you can think of it as picking up noise, or maybe picking up patterns that aren't really a human concept. Oh my gosh, plate notation. So I remember this being scary the first time I looked at it, but the more I work with it, the more I see why people do this. This is a graphical model of a probabilistic process, and this is LDA, the algorithm we just looked at in that language. And this looks horrifying, but actually when you start working with this a lot, this is a pretty, this helps clarify things. So here's how you read this. So circles are variables, random variables. Filled in circles are observed. So the only thing we observe in all of this is the words in the document, right? So this is the nth word in the dth document. It's the only thing we observe. A box around it with a subscript means repeat it that many times. So in this case, we have n documents, we have n words. So we repeat this word thing n times. And we have d documents. So what this is saying is we start with these parameters on the left and right, which just tell us how concentrated we expect the topics to be. And then that from that we sample the topics for the document, once for each document. And then in each document, we pick from that distribution of topics, we sample from the words in the topics, that's this D thing. And finally, we generate the word using the words in the topic, or the topics, distribution of topics for the word, and the distribution of the words in the topics to generate that word. And on this side, we have k topics. Each of those has a certain set of words, and those have some distribution according to these parameters, these hyperparameters. These are actually formally, these end up as priors in the Bayesian sense. So I think most of you are familiar with the idea of a Bayesian prior. If you've done machine learning, you can also think of them as regularization parameters. They guide the algorithm towards a certain type of solution. So the reason I'm showing you this horrifying diagram is because we're going to look at more horrifying diagrams like this later when we talk about recommendation systems. In fact, the New York Times recommendation system is best described with a diagram like this. So that's why I'm trying to introduce you to this notation. And this is also, I don't know, this is a life skill, man, plate notation. You'll be able to read papers you wouldn't otherwise, let's put it that way. Okay, let's talk about actually computing this thing. And the reason I'm actually showing you this algorithm is because I don't want this to be magic. I want this to be something that you feel like you understand and could implement in 20 or 30 lines of Python. And so I'm going to show you the classic algorithm to do this. So here's the idea, right? The inputs are the actual text, the number of topics, which we specify as a parameter, and then these two hyperparameters, A and B. And also a few other things, right? So we have the number of documents, we have the number of words in each document, and the vocabulary size. So the vocabulary size is just the size of this matrix, right? So this is V, this is N. And then the length D is just the number of text. So far, so good? And this is what we're going to compute as the output. We're going to compute a topic assignment for every word, and then we're going to compute the distribution of the words in the topics, which is this matrix, and the topics in the document, which is this matrix. Now, we're not doing matrix factorization, so we don't actually literally multiply these together. Instead, what we're finding is we're trying to find the set of topic and word assignments that produces the observed documents with the highest possibility. So we're actually doing a maximum likelihood estimator here. We're trying to figure out how do we pick these things such that according to this theoretical process, here it is in plate notation, here it is in English. So according to this theoretical process, that we should pick these probability distributions such that the actual text that we have occurs with the highest possible probability. So it's not a matrix multiplication, but it's a similar idea. And this is how we do that. So this is the initialization. We start with setting the distribution of words in each topic to be some constant. Right? This is the parameter. So this is actually where this sort of the topic word concentration comes in. If we set this very high, what we're saying is, well, this distribution of words in each topic is relatively flat. If we set it to 10, we're saying, well, we have an equal chance of every word in each topic. And then once we have the topic assignments, right? So let's say we know, what are we doing here? Yeah, so say we know which topic each word is, we can compute topic words. So if we know the assignments of topics to words, we can just run through every word in every document and count how many times each word appears in each topic. That's all we're doing here, right? So we're just starting with this initialization and saying, well, just as a baseline, each word appears in each topic b times. But then we're actually running through each document and each word in the document, and we're saying the topic that this word is assigned to, the word that this is, add 1. And then we just normalize the thing so it's a distribution, right? So that should convince you that if we have this assignment of topics to words in the text, we can produce this distribution of words and topics. And then going the other way, again, if we have the assignment of topics to words in the text, we can produce this distribution of, well, what are the topics in each document? Right? Exactly the same logic here. So then what we do is we go back and forth between the two. First, we assign a new topic to each word in each document by sampling from the topics in each document, which is this, times the probability of the word in the document. And some of the possible topics we could choose will rank very highly because either it's a very common topic and that word is very common for that topic, and we sample from that according to the probability. Right? So this is where we walk through and assign a topic to each word, and then after we've assigned a topic to each word, we go back to these two steps and rebuild the words in each topic and the topics in each document. And we go back and forth between these two steps. So in other words, if we look at this diagram, first we assign a color to each word. And then based on the colors we assigned to the words, we go back and recompute what the distributions of words and topics are and what the distribution of topics and documents are. And then we repeat. And each time we assign this color, we pick from the distribution that is implied what is the probability that we pick yellow. Well, that's the probability that this is a yellow word times the probability that a yellow word is the word Jean. Okay, what is the probability that we pick purple here, right? It's the probability that this is a purple word times the probability that a purple word is the word organism. So I go back and forth. same idea. I update the words, and then I update the distributions, and then I update the words again over and over. And this actually converges. You can prove that this converges. And what I get when I'm done this is this set of topics in the documents and terms in the topics. Okay, why do I bother doing this? This fancy algorithm. You can think of it as a dimensionality reduction trick. When I compute a tf-idf vector, I have a vector for each document that is the size of the vocabulary of the document set. And so if I have a few thousand documents, that's easily 10, 20,000 dimensions. It's a little hard to work with, and it's very noisy. And I don't really want dimensions for words. I want dimensions for ideas. And so when I run one of these algorithms, what I get is a much lower dimensional space, maybe a couple hundred. And then when I have these lower dimensional vectors, right, which are these, again, these topics for each document, then I can do all of my normal tricks. I can do cosine distance between them. I can cluster them. I can visualize them. All of the stuff that we talked about. And it's likely to be more accurate because now I've resolved synonyms. Right? Now I'm not matching. I had this problem before where I wouldn't be able to figure out that a document that only said HIV and a document that only said AIDS were talking about the same thing. Now they're going to be assigned to the same topic. So this gets us closer to this idea of conceptual similarity. Okay, I know that's a lot to take in. So let's talk about this for a little while. You can also do things like this. This is a very popular use of topic analysis to make these sort of stream graphs showing topics over time. This is, my students in various classes always want to do this, and in fact you're going to do something like this for the homework. The idea here is that you do topic modeling of the entire data set, and then you break it up into years, and you ask how many documents are in each topic for each year. And to do this, you have to assign a single color to each document. So normally what you do is you just take the topic that scores highest for each document, and then you draw it. And you can see what a topic actually is. It's the same thing, right? These are the top most probable words for each of those topics. Okay. We're going to look at yet another vectorization technique. This is word embedding, which Alex, you mentioned. So we've now gone through this history. We started with tf-idf in the 1970s. This was the first document vectorization method. We moved into the 90s with matrix factorization, and then the early 2000s with probabilistic topic models. Now we're getting up to the neural network era. So all of these things will work, but as you sort of get increasingly sophisticated, you solve certain problems. Word embedding. How many of you have heard of word2vec? Yeah, that's what this is. So to motivate this, here's a case where word embedding was used in a public interest investigation. So this is a post that is referenced in your syllabus. It's an analysis of the comments on the recent repeal of net neutrality, the comments to the FCC. And there was an enormous amount of robo-submission, largely but not entirely on the pro-repeal side. And previously what we've seen is hundreds of thousands of identical messages in previous comment periods. We saw some identical messages, but we also saw this. We saw hundreds of thousands of not identical messages. And it looks to me like whoever did this was trying to evade detection, right? They were trying to evade any tool that looked for identical messages. So you can see what they did, a kind of Mad Lib, right? So sometimes it says Americans, sometimes it says individual citizens, sometimes it says so-called experts, sometimes it says the FCC, sometimes it says Washington bureaucrats. And just sort of substituting these words in a template form. And this data scientist found this when looking at the data and then wanted to cluster them. So the issue is, if you do tf-idf, these are not going to cluster. These will have high cosine distance because two of these sentences may not have any words in common. So instead we have to cluster based on the meaning. So we need something that captures the meanings of words. And this is why they used word embeddings. So here's the idea. A word embedding is a function that maps a word to a vector. The vector typically has a few hundred dimensions. The hope is that words which have similar meaning have similar vectors, so that cosine distance becomes a semantic operation, right? So that is always our hope when we do this vectorization of text. We always hope that we can build a distance metric that captures semantics of interest. And there is no guarantee that tf-idf or LDA or any of this stuff captures anything we care about. It's just that empirically, it kind of does. To generate word embeddings, we take a bit of a different approach. So in order to avoid thinking about this, I've copied the definition of distributional semantics from Wikipedia. But distributional semantics is a linguistic theory of meaning. And it is a theory of meaning that says that the meaning of a word is exactly the distribution of words that appear with it. So, two words which are used in exactly the same places in exactly the same sentences have to be synonyms when you look over a large enough corpus of language. That's the idea. A word is characterized by the company it keeps. That's the idea. So, if you believe distributional semantics, well, let me back up. In some sense, distributional semantics has to be true because for the most part, there are some exceptions such as words that sound like what they are, onomatopoeia, right? Those have some tangible relationship to the physical world. There's a reason we have that word and not another. But the majority of words, by far, there's no reason that particular word means that particular thing. And you can see that because in other languages you use another word for that particular thing, right? So in some sense, the meaning of a word can only be the relationship of a word to other words. It can't really come from anything else because it's certainly not in the word itself. That's the insight there. The meaning of the word is not in the letters that make up the word. Yeah.
But doesn't that disregard etymology?
Yeah, so there's this historical context, right? So it came from someplace, but etymology just pushes the problem back a few centuries or millennia. It's like, okay, fine, so we can trace the root of this word back to Indo-European, but why did they choose that word? Right. And I mean, there's some historical event which shaped the choice of that word, surely. But the existence of multiple languages tells you that that's not where the meaning comes from. It doesn't come from the letters in the word. It doesn't come from the pronunciation. It doesn't come from the etymology. It comes from something else. It comes from the way it's used to refer to stuff. So that's the basic idea of distributional semantics. And if we believe that, then we should be able to capture the meaning of the word by analyzing the distribution of the words it appears with. That's one concept you need to understand word embeddings. The other is the concept of an autoencoder, which is one of the coolest things in neural networks. So autoencoders. Autoencoders are originally appeared in data compression. Here's the idea. Let's think about a compression algorithm. The basic idea of a compression algorithm is that you have a bunch of inputs and you do some processing and you have a smaller number of outputs. So, these could be bytes in an image file, they could be data representing human speech and so forth. So for example, these are pixels and these are bytes of a JPEG file. Or these are samples and these are the responses of the MP3 filters, right? This is how codecs work. So this is an encoder. And then a decoder is the reverse, right? It takes the small number of inputs and reproduces as closely as possible a much larger number of outputs. So there is a whole field of engineering, which is the design of codecs. How do you do this such that the output most closely approximates the input? So you design your encoder or your compressor and your decoder and your decompressor. Great. And historically, most codecs have been designed by hand. Someone sits down and figures out a coding scheme. But, you could just make this a neural network and then connect the encoder directly to the decoder, as you see in the image here. And then you train the neural network so that the output of the matrix is as close to the output of the network is as close to the input of the network as possible. You just say, figure out the weights yourself. You're asking it to design a code, right? A code that the encoder creates and the decoder reads. And to do this, it's going to have to figure out similarities between the possible input values, right? So if you train this on speech, let's say, and this is some number of samples, this is like a half second of human speech or something. Rather than sort of thinking about speech at the sample level, you're going to think about it, well, it's got a frequency, and it's got a volume, and it's got a sort of filters created by your throat, which control the frequency response. It's got a noise channel, which is, tss, all the fricatives and hisses. And so maybe if you use this for speech, it's like, well, this one becomes the frequency, and that ends up being volume, and that ends up being hiss amount, right? But you just let it figure it out on its own. That's the beauty of this plan. When you do this and you look at what actually happens, you can see that it's figured out. If you do this with image, you get things like edges. If you do this with sound, you get stuff like this. We're going to do it with words. So this, finally, is the word embedding, how you build a word embedding. From, again, one of the references in your syllabus. This is a model called continuous bag of words. And what this is you slide a window over the text. So it's an odd-sized window. So here it's size 5 window. I think in practice you'd want to use a little wider. And think of it this way. You feed in on this side the words on the left and right side of the window. And on the output side, it has to tell you what the central word is. And you design the network so it has this bottleneck in the middle, right? So if the input is the words in window, and the vocabulary size is 10,000, there's 10,000 possible words, and we have a window of 2 on each side, then what we have is 5 times 10,000 is 50,000 inputs. If you use one-hot encoding. You all know what I mean by one-hot encoding? So one-hot encoding is, I tell you which word it is by having a 1 for the input that corresponds to that word and a 0 everywhere else. So if I have a vocabulary of 10,000 to represent one word, I need 10,000 inputs. And if I have to represent 5 words, I need 5,000 inputs, or 50,000. Actually, I'm off by 1 here. I don't give it the central word, so it's the 2 words on the side. So 4 times 10,000. So I have 40,000 inputs. And then I have, let's call it 200 for the code size. So I have to somehow capture all of the information in these 40,000 inputs representing 4 words in 200. And then I take those 200 and I have 10,000 outputs representing my guess of which word comes out the other side. Same thing, one-hot encoding. Although what I'm actually going to get is a probability distribution, right? I think it's like 50% that one and 20% that one. And the thing to note is that this part in the middle is super small, right? It's dramatically smaller than the rest of it. So the only way that this can make good guesses is by figuring out common patterns. So, we train this thing, and let's use our traditional example. And this dimension in the code may end up being the HIV dimension, right? So words like HIV and AIDS, which will appear with similar windows around them, will end up getting mapped to the same neuron. So we train this entire network so that it guesses the word in the middle as well as possible. And then what we do is we take scissors and we snip it right there. And then we use this smaller output as the vector. So far, so good? Any questions? This works shockingly well. In fact, it works so well that the vector dimensions end up having semantic interpretation quite commonly. So here's a classic example, and this is a relation you basically always get. There's different ways to train word embeddings. Obviously, you can do it on different source text. The only thing you need to train this is a whole bunch of text, right? Lots and lots and lots of text. And so what you discover is that if you look at the vector between man and woman, if you do woman minus man, that's going to be the same vector as queen minus king. And so it's actually, what that means is it has actually produced a gender dimension. So one of these output neurons ends up being gender, or something like it. Could be a combination of them encode gender. And the reason that happens is because if you think about predicting the word task, if the thing in the middle is a noun, say it's going to be somebody's name, and you know the gender, that gives you a lot of information about what that word's going to be. And so it really helps the predictive accuracy to have some sort of representation of gender. So that's why that happens. But there's stuff that you maybe wouldn't expect, like there seems to be some idea of the capital of a place too, because you can do this other thing. You can you can think of this as a metaphor. Paris is to France as Poland is to, and the word embedding will tell you Warsaw. And these equations, they're literally equations for the vectors that you get from running this mapping function. So that tells you that this has really captured a lot of the human semantics. Interestingly, this also captures stereotypes. I mean, it has to. And we'll get into this a lot more when we do algorithmic accountability stuff. But this is from a fascinating paper talking about gender and word embeddings. And if you do this same type of formula and you say, okay, man is to computer programmers, woman is to, and you get what you get is something like homemaker, right? Which should surprise nobody. But it's interesting that this encoding process will pick up that stereotype. And in fact, it will pick up that stereotype no matter what text corpus you use. This was initially trained on Google News articles. So even when you train this system on professionally produced news articles, you still pick up these ideas. They're in there. Right? It's kind of amazing how to do this complicated mathematical analysis and have it discover that basically all text has these stereotypes embedded. I think there's some really interesting cultural consequences to explore there. But you can see some of these stereotypes that it figures out, like vocalist guitarist. That's kind of amazing. But apparently vocalists are female and guitarists are male. And then what this paper is about is that you can actually try to remove some of these gender biases, right? So here they're using softball, football as the gender axis because they found that softball is very female and football is very male. So what they actually do is they take the direction from softball to football, so softball minus football, they call that the gender direction. And then if you subtract that off, just like going from king to queen, you go from, looks like receptionist to major leaguer. It looks like the sports stuff is still leaking in there. Anyway, so people are trying to sort of analyze how these stereotypes work. I find these fascinating. I'm sure we're going to discover tons and tons of weird things about language by looking at this stuff.
What did they use to train?
They tried a few different training sets and got essentially identical results. So they tried with Google News articles, and then they tried with, I can't remember the other data sets they used.
They were similar.
Large corpuses of text. Wikipedia, I think, is the other one. Yeah. So this stuff is super deep in the language. Yeah. So you've got this word embedding thing. Going back to the FCC comment example, this is the where they talk about how they did it. And so you have to read the footnotes. But here it is. Comments were turned into document vectors comprised of the average of all word vectors in the comment. So they run the embedding on every word in the comment. They sum it all together to get the average meaning of the word, I guess. And then they cluster on those. And that clustering algorithm found this. Clustered all these together.
Do you remember what the numbers were? The percentage of comments that they
Uh,
comments?
I don't remember it as a percentage, but as the title says, more than 1 million. It was the majority by far. And then on the anti-repeal side, there was a bunch of form letters too. That was mostly like an EFF campaign against it. So I mean, it's not a shock that people are doing this. What is interesting here is they're trying to hide it. This raises some fascinating questions about how do you interpret comments on proposed legislation in the era of machine-generated submissions, right? What do you count? What do you do? I'm sure that the FCC is now using tools like this to break down yeah, okay, so we've got 500,000 of these, but they're all the same thing. But this is a particularly sophisticated one. And it's meant to fool a naive clustering tool. But, you know, with the power of deep learning. Okay. I want to jump from really complicated stuff to much simpler stuff. I want to try to convince you that counting words is still a very worthwhile thing to do after all of this like feature embedding fanciness. Here's a story I did for Neiman Journalism Lab. Those naive times before Trump was even the candidate. But already he was producing a lot of media at the time. And what I did is I looked at the primary polls. So this is January 2016. And the media mentions, and showed that there was an almost perfect correlation between their polling numbers and how often they were discussed in the media. Which it turns out political scientists have noticed before. But I find this totally fascinating, and you know, then that gets into a whole discussion about media influence, which is a discussion we will have. One of our later classes is going to be on media effects. And to do this, I used Media Cloud, which is a tool maintained by the Media Lab at MIT, and basically sucks in a bunch of media sources, including now transcripts of broadcasts, and will do things like word frequency plots and entities that appear, and you know, really a bunch of fun stuff, but basically all counting, right? Nothing more than counting here. Similarly, how many of you know Google Ngram Viewer? So here's one of my personal favorites. You can see the relative popularity, or at least the rate at which they were discussed in books.
Can you throw in alcohol?
Oh yeah, I bet that's much higher. Yeah. So you can see the peak of cocaine in the 80s. You can see the peak of LSD in the 60s. Right. So all this is just a huge database of n-gram, comma, number of times in the corpus, and also they have number of times in the corpus and also number of pages it appears on as a different way of counting. So there's quite a lot you can do with just like this very simple idea. So I'm gonna show you one of my favorites. So this is a guy, he was at Princeton at the time, who was a computational linguist who liked Downton Abbey, and you know, people were saying, oh, that word wouldn't be used at that time, and so I love that. I lack such social graces, so I thought, why not just check every single line in the show? So here are some words that are in the scripts that don't appear between 1912 and 1921 in the Google Books corpus. And he used the Google Ngrams corpus, which we were just looking at. He just downloaded it and did it.
Isn't that a little biased because those are books and it's more property-ish?
Yeah. So there's this famous line, I wanted to study the history of ideas. I ended up studying the history of books. So yeah, it's books. And here's stuff that does appear, but vastly less commonly. So black market, I think, is the most interesting one. I would have thought that's a very old word, but apparently not that old. Or you can just plot all of them. So here are all the n-grams, and here's the frequency in Google Books, and here's how the relative frequency in the text in the show. Now, to interpret this graph, we have to basically anything that's high up in this graph is going to be suspiciously common, therefore anachronistic. But we should expect that this graph follows a shape something like this. Just because these start to be very low counts, there may be only a couple times in the entire sample. And so the variance starts getting very high to the left here. So the null distribution of just random words is going to have some funnel sort of shape at the top and the bottom. So to really interpret this graph, we'd have to put sort of the shape of the null distribution on it. And then we can sort of look at like p-value stuff, right? Things that are above that line. But anyway, there's this fun stuff here, like, maybe even. Apparently that is overrepresented by almost 100 times. So who knows? Anyway, there's a ton of things you can do with just text analysis. The first thing we'll do is talk about stuff that standard NLP techniques don't address very well in journalism. So these are sort of, you can think of this as domain problems for journalism. And standard methods they're not far off, right? Many of them will work in some way. But there's a bunch of stuff that we have to think about if we're trying to do this stuff in journalism. So this is in the context of the document mining stuff that we were looking at last week. Mostly in that context. The first thing you will discover when you start doing this is that something that in computer science we sort of take for granted is extremely difficult in journalism, which is actually getting the data. So you may have to file a Freedom of Information request. You may have to convince someone to give you the data. There are entire classes devoted to how to get this information. I'm involved in a class at Stanford called Big Local, where the students are getting public records from, like the same type of records from a variety of different cities and combining them. And that is quite a process. Some cities will just have them available for download. Some cities will require a FOIA request. Some cities require negotiation. If they give you it for a FOIA request, they might want to charge you, so then you have to negotiate for how much money it's going to cost. You'll get answers like, well, we have to write a custom database query, and our engineer says it'll take 80 hours, and then you have to get someone who knows how to write SQL and be like, that's bullshit. This is an hour at most to pull this table. Even things which are supposed to be public records or are public records are often not available in bulk. So the corporate registries of several countries, notably Hong Kong and basically all the tax havens, you can get the registration information for a company, such as it is. But for example, Hong Kong wants $10 per record, right? So you can't write a scraper to get all of it and then do like network analysis or pattern matching stuff. You have to get one record at a time. Some of this is automatable to some extent. So there are tools like Muckrock that help you file Freedom of Information requests. So you should definitely check those out. They're basically they have a form letter, they give you some instructions on filling it out, and then they route it to the right place. They know all of the laws about how long they have to reply. They're quite nice. And Muckrock is now merged with Document Cloud, so your documents will actually show up in Document Cloud. Assuming you can get the data, you then have this problem of what does it mean? And even if the documents are ostensibly English language text, you will find that they are not really English. So this was, we may have seen this earlier, this was that LA Times story on the police misclassifying crimes. And so they ran a classifier on all these incident descriptions, but the incident descriptions look like this, right? They're this weird, almost English type of thing. And this is super common. Even if you have full sentences and complete words, you're going to have weird vocabulary. So if you're reading financial documents, it's going to be idiomatic, and it's going to talk about certain types of things. It's going to have lots of abbreviations, right? does your parser know that a beta is a noun? That's, what is it, earnings before, earnings before debts, income, and taxes. Anyway, I can't quite remember what that accounting term means. So you're very often going to have to train a custom domain model. Another issue is that the data is just nasty. This is some of the Iraq data we looked at last class. So fun stuff, right? We've got handwritten annotations. We've got redactions, old school style, where they actually cut out the words with an X-Acto knife and then photocopy it. We've got holes punched through it. We've got some actual handwritten content, as we saw. By the way, the little markings next to the paragraphs where it says 67F, what that is there are only a few legal reasons, I think 5 reasons, why you can remove information from a Freedom of Information request, why you can withhold information. So what that is that's actually a notation indicating the subsection of the law under which that information is withheld. So that's why this took, let's see, we got the information in 2010. Yeah, more than 3 years to get this stack of paper. It's because they had to do this with every single page. On the right is what it OCRs to. Now this is using Tesseract, an older version of Tesseract. So you can get better, right? You can do better OCR than this by using a commercial library. But you're always going to have these problems, right? So any algorithm which assumes that things are spelled correctly is a non-starter. Even problems which in the NLP literature are considered more or less solved in the sense that they are mature technologies with many commercial vendors don't necessarily work accurately enough or the way that journalists need them to work. So how many of you have played around with entity recognition? Yeah, okay. So we'll actually have an assignment on entity recognition. We'll play with it a little later. Entity recognition, like all classifiers, is tuned to balance precision and recall. As such, even on commercial services on clean test data, you get about 70% recall. So I mean, we're talking, Google and Microsoft, right? This is not like open source libraries. This is commercial services. That level of recall is because they're trading off against precision. They don't want to include stuff that isn't really entities. Unfortunately, for doing journalism, especially investigative journalism, you want the trade-off heavily skewed towards recall. So you would much rather have near perfect recall and have a bunch of junk. And that is because when you're doing an investigation, the journalist is chasing down leads anyway. Right? So you normally use these types of techniques to generate a big list of people or companies or places or dates which could be interesting, and then you run each of them down manually. Or maybe you match them against another list. We'll talk about list matching and list filtering operations. It's a basic investigative technique. And because of that, what you really want is false positives, not false negatives. So in principle, you can tune these algorithms for high precision, high recall and lose precision, but they're not normally set up that way. Another fascinating problem with entity recognition is that, so in your NLP classes and in the research literature, you will learn about doing NLP by parsing. So basically you build a model of the natural language, English or German or whatever it is that you're doing. And that model parses out the sentences. And it's kind of like the reverse of a Mad Lib problem, right? If I say, the location of the meeting was X in the third canton in Switzerland, then X is a place name. Well, that's fine, except that a lot of the entities you want aren't going to be used in sentences. So part of speech-based tagging or parsing is not going to work. And so here's a very simple example. This is from a document describing the structure of a Russian telecommunications company, Vimpelcom. This is actually part of a story about money laundering in Uzbekistan that the Organized Crime and Corruption Reporting Project did a couple years ago. And so what we need is those list of names, right? So those don't appear in sentences. So basically, every NLP package, at least all the open source ones, will just miss that entirely, right? And all of this stuff about like conditional random fields or sort of, building up classifiers based on parts of speech and so forth, it just doesn't apply. Now, in principle, you could train a system to extract this stuff. People are just beginning to apply deep learning approaches to form extraction. So rather than treating the document as a stream of text, you treat it as, stream of pixels is a bit too low level, but you can treat it as a stream of text boxes. So this is now text with bounding rectangles. And that lets you figure out that something is a table of names. And you should be able to train a deep learning classifier to identify tables of things on pages and maybe see, oh, all of these, most of these things have LLC in them, or maybe they have the word subsidiary above it like they do here, and generally figure out that what you're looking at is a list of company names. It should be possible. I know some of you are messing around with some deep learning stuff. This would make a fine final project to attempt that. So actually good NER is an incredibly contextual problem. You have to not only extract those strings, but resolve among the synonyms of those strings. And you can only do that by looking at all the other text in the document.
So all three are like equally bad?
I don't want to say equally bad because I haven't tested in any great detail, but they're all kind of crappy, yeah. So it's not to say that these problems can't be solved. It's just that in practice they aren't solved, and the CS literature tends to ignore these problems. So one of the things that I like to say is a document is not a string. A document is a much more complicated object. And one of the reasons we have these problems is because too many investigations or algorithms of this problem consider that this is a document, right? It's a bunch of characters, when in fact it's this much more sophisticated object. I mean, and I'm guilty of this too, right? Because if you can get it to a string of characters, it's much, much easier to work with. I've only very rarely used bounding box representations.
What does that mean exactly? So bounding box where you only just know the position of the text, and then you just create a rectangle around that? Or?
Yeah, so there's various formats. So for example, Tesseract will output something called HOCR. And what HOCR is, it's basically just a list of strings with bounding boxes. Right? So you know where everything is on the page. And that geometric information gives you an enormous amount of insight into the structure of the document.
That's not the same as pixel.
I mean, yeah, it's pixels. It tells you, I mean, I don't think it's actually expressed in pixels, but it tells you where on the page it is. Yeah. But it's not, so for example, if you were doing, training a classifier on this information, you don't feed it the raw pixels, that's too low level. You feed it the OCR strings with bounding boxes.
A bounding box is just a list of coordinates for
Yeah, it's just a rectangle. Yeah. So you have a rectangle for each of the strings that it found on the page, so you know where they are. Yeah. And normally that's invisible, right? Normally the OCR pass, I mean, it computes all that stuff, it has to, but it throws it out. So what you want is you want the output from an earlier stage in the OCR pipeline. And when I talk about these problems with NLP researchers, they tend to sort of go, oh, that's just OCR. I mean, okay, fine, it's OCR, but it's still an unsolved problem. Another challenging problem in journalism is that Usually when you're looking through a large set of documents, you're looking for something, but the thing you're looking for may not be easy to search for. It may be paraphrased in a complicated way, meaning that text search won't work. So I wrote a paper where I said, what we do with document sets is mostly not explore the document sets, which is what most visualization, like text corpus visualization approaches talk about. We're going to explore this set of articles, right? Normally you bother to go through the effort to get the information because you're looking for something. But just because it's a search problem doesn't mean that you can use standard text search. So this was part of a story by Adam Playford, then at Newsday. What happened here is there was a union dispute such that there was not a coroner on duty overnight at the time, which means that when somebody got stabbed, the body just lay there on the sidewalk overnight. So the city, actually I think this is county, yes. The county meeting transcripts contained a reference to it. And Adam actually read through thousands of pages to find this. And he was looking for other things too, but this is one of the things he was trying to find. And this is the only reference to that incident. And you can see how elliptical it is, right? So the incident, I believe, in the Brentwood area. And so you might have been able to find it with Brentwood, with the location. But if you search for body on the sidewalk, you don't get it. So, euphemism. The way I like to talk about this is that when you finally get that secret cache of internal documents of your suspected money launderer or your corrupt politician, you can't just search for bribe. Right? You can't search for corruption. It doesn't work like that. Although, actually, when the former Ukrainian president was deposed a few years ago, Yanukovych, as he left his mansion, he dumped thousands and thousands of pages of documents into the lake. And journalists arrived a few hours later and actually had divers fish these documents out of the lake and lay them around the mansion and blow dry them and then scanned them all and put them online. And it's still online. It's called Yanu Leaks. Maybe it's no longer online. Oh, well, here's me writing about it. This is writing about how much the Pulitzer Prize involved document mining in 2014, including this story that overview was used for. There you go, the Yanu Links documents. Let's see if this link is still working. Yeah, here we go. We'll translate it. This is a crazy story. If you want to get into like guerrilla journalism, you should check this out. Yeah, so there they are, right? So these are these documents drying that were at the bottom of the lake. And I was told by one of the journalists working on this that a lot of this stuff was accounting records, and they actually found records that just said bribe. So here you go, exception that proves the rule. Occasionally they will just say bribe, but generally they won't. So now this is a solvable problem as well. There's lots and lots of techniques for sort of paraphrase detection. So for example, word embedding is one technique to do this. If you took a word embedding of all of the words in this document, maybe you would get it, right? Maybe incident and homicide and so forth. I don't know, you could imagine search algorithms that would find this type of thing. The final thing I want to talk about on this topic is that the problems that journalists have to solve when we do these big document analyses are well beyond the state of the art. So how many of you are aware of the reading comprehension research that goes on? This is normally what this is called, or general question answering. The idea is you feed a bunch of text into the machine and then you ask questions in natural language and it has to give you the answers. And so a famous example of this is the Watson machine that IBM built to play Jeopardy. So we've moved well beyond that, but we're still not really at the level where this is useful to journalism. So let me show you a real-world example. This was actually a big class project at Columbia last spring. And yeah, that's right. And what the students were doing is they were investigating Trump's properties in New York and starting with the question, who owes how much money? You know, who owns the building? What's the outstanding debt? What's the equity? Just what's the capitalization structure of each of these properties? Because that will tell you who's involved in financing them, and then you can go out from there and you know, look for irregularities. And so this is public record. You can download these documents one at a time from ACRIS, which is the New York City real estate database. Being computational journalists, we wrote we used browser automation to scrape the 20,000 or so documents that related to these properties. And on each property, you have several dozen documents, and they look like this, right? They are legal contracts. And in principle, all you want to do is you want to add up some numbers and figure out how much debt is outstanding. So this is what it looks like when you do that. This is a handmade spreadsheet which tracks who borrowed how much money when. The colors are used to organize documents by date. So the documents generally occur in bundles, which represent the closure of a deal between a bunch of parties. And it goes on like this for a few dozen rows. And it's a well-defined problem. There is a correct answer, right? This is not a subjective question. The answer can be arbitrarily complicated because the deals can be arbitrarily complicated. It could be how much money is owed. Well, you know, 20 million to this person, 10 million to this person, and then 18 million to this person, you know, except it might actually be 12 million if they exercise their option for the air rights before 2018, right? So the contract structure can actually be very complicated. So although the answer is well defined, the form of the answer is not necessarily structured. Representing it is going to be a challenge. And we'll actually have a class on knowledge representation. So this is a very hard problem for a computer to solve at the present time for a variety of reasons, one of which is that the training an algorithm to do this is not possible at the present day because the available data is a few order of magnitudes too small. So on each property we have, let's say less than 100 documents. We have a few dozen properties. So we're talking on the order of 10,000 documents. We could include all developments of this size in New York. I looked through New York City statistical information and found that there's probably a few thousand buildings or developments of this size in the city. So, we might have 100,000 documents total. For each of those buildings to generate the trading data would take a dozen hours of work to generate a spreadsheet like this. So it's a huge amount of work to generate the training data. And then you would have a few thousand examples. Modern question answering sets, such as the Stanford question answering database is 100 and something thousand. And then there's one that's extracted from Daily Mail and CNN articles, and that's 1 million and something. So we are at least 2 orders of magnitude too small, just in terms of training data, and then the problem is too complicated. We're nowhere near being able to do this type of work. So that's the bad news. The good news is there's lots of room for experimentation and improved techniques, right? Like, we can only get better at this. So lots of fun research. And part of what I'm trying to do is assemble training sets to encourage the NLP community to study the problems that journalists have. This is one of the reasons we haven't solved these problems, is because you know, I go around and give this talk to computer scientists, and most of the time they've just never seen these types of problems. And they don't have a data set to write papers on. Oh, okay, well that's the end of that. Okay, any questions on all of this material before we move on?
I know you said word embeddings could help, but I
Mhm.
didn't understand how. If you could explain.
So, okay, so word embeddings may be able to help in these search problems because they capture synonym information. So two words which mean about the same thing are going to have very similar vectors. And the reason they're going to have very similar vectors is because two words which mean nearly the same thing are going to be used in very similar contexts, which means that in the bottleneck, when we train it and we reduce it from tens of thousands to a few hundred, it's going to improve the accuracy greatly to map those two words to the same dimension. So if you, so do you remember the example last time where we saw all of those FCC comments that had slightly different wording? So word embedding was able to find that those comments were the same because it can detect synonyms that way. So we're starting to get like synonym search methods.
Does it work in this case when you're like, this is exactly what I'm looking for, and not on like the topic?
Right, yeah, well, you want the search to match topics, but it's not going to match topics if you just do normal word search, right? So like tf-idf. So most modern search engines will actually handle synonyms. So Google will do this, for example. It knows, it'll actually resolve both synonyms and homonyms through techniques like word embedding and so forth. All right, anyone else? Okay.